Hello guys, in this video today we are going to discuss about continuity equations for electrons and holes. So as the name suggests, you all must be knowing continuity equations. What is the meaning of continuity equation? So continuity equation is one equation, mathematical equation is a form of equation where you can relate the variation of a particular variable, okay, the change of a particular variable with respect to time and how it is related to the variation of that particular variable with respect to space. So for example, if I will say x, some y is the variable, for example, okay, y is the variable, then we need to find out how this y actually varies with respect to time. Okay, so it is particularly a variation of this kind, the variation here I can say y can also be function of other variables. Y may be dependent on all many other parameters, but here if y is a function of space and time particularly, right, then we are just trying to relate this variation of y with respect to time, and how is it related to how is it related to what the same variation of y with respect to the position. So del y by del x and del y by del t, okay, something equivalent to this kind of a equation we call a continuity equation. Okay, so here in this video we are going to write the continuity equation for electrons and holes. So when I said I'm going to write or I'm going to discuss the continuity equation for electrons and holes, definitely we are going to write the continuity equation for electron concentration and hole concentration. Okay, so I hope you understood what do you mean by continuity. Okay, continuity equation. So here we are going to establish the relationship between the concentration of electron, okay, with respect to the variation of concentration of electron with respect to space, and how is it related to variation of electron concentration with respect to time. The same we will do for holes. Okay, so this is the objective of this particular video. So now here, suppose I'm going to show you a volume element or differential volume element of this kind, or differential volume element I'm drawing. Okay, so here you can see all the three dimensions, all these three dimensions. Let us take dx, dy and dz. Suppose this is your dx, okay, infinitesimal small dimension we have considered. Similarly, if I'll just write this is your dy, you can say this is your dy, and then dz. Suppose I will write this is our dz. Okay, so now you can see all three sides I showed you, dx, dy, dz. This is the infinitesimal small volume element I considered. Okay, now here suppose we will show that the flux is moving in the x direction. Okay, x direction. What do you mean by this? This notation I'm using. Let me use some other color here, light bright color. So here this. Okay, so let us consider the flux. Okay, flux of holes, okay, moving in this direction, x direction, right? So the amount of flux that enters in the x phase here, this is the x phase here, you can see. And now this phase is x plus dx, exactly opposite to that, x plus dx. That means it traveled a distance of dx. So here I will write the flux that is entering is fp x, suppose I will write, and the flux that is this is entering, the amount of flux entering here, the amount of flux left here. Okay, this phase, okay, that is, suppose I will write fp, and the change is x plus dx. Okay, there is no change in dy and dz as it is moving in the x direction. So this way we can write. So what I said, the fpx here I said is the whole flux. Okay, and what do you mean by whole flux? If I will say the concentration of holes, or I will write the number of holes, okay, per unit area. As we all know what is flux, Okay, so flux means what? Something, number of lines of forces. You said, electric flux, number of magnetic lines of forces. You said flux, magnetic flux. Similarly, so number of holes per unit area per unit time. So this is what we define, this FPX. Okay, so FPX is the number of holes or hole flux we said, or number of holes per unit area per unit time entering at X, entering at X. Okay, similarly, if you want to write what is a px plus dx, you can write this is number of holes per unit area per unit time living, okay, at x plus dx. Okay, so here all the other things will remain the same. Here only the additional term I said is x plus dx, living at x plus dx, number of holes per unit area per unit time living at x plus dx. So these are the notations we can use, right? Then what we can find out is to establish the relationship between the variation of concentration of holes, okay, with respect to x and with respect to t, and how they are related. We can use what we can use is, we can find out the net change in the number of holes per unit time, okay, within that differential element, with differential volume element. So that is what we are going to find out. Okay, so now if you will see, what I said is FPX. Okay, so FPX we said is the number of holes per unit area per unit time, per unit area per unit time, per unit time. Now the area, if you'll see the area that it is entering through. Okay, so you can see this area, if you'll see, this is the area, right? So this area, if you'll see, this is dy and dz. You can see this face, this particular face, right? So this particular area, if you'll see, okay, this is the area. So x is the variable, the area here is actually dy dz. So dy dz is the area through which the flux fpx is entering, right? So now we can write fpx is number of holes per unit area per unit time. So what is the per unit area over here? The area we said is actually dy dz, right? So now what we are going to find out, we are going to find out the net change in number of holes per unit time within the differential volume, within the differential volume. So what is the differential volume? The differential volume is dx, dy, dz, if you see. Okay, so in that the differential volume, number of holes per unit time, per unit time, if I want to find out, then I can write what is the value here, that is entering will be what? Entering will be what? Fpx you got. This is your per unit time per unit area you said. Now through that differential volume means you are talking about area dy dz. So dy dz will be multiplied here through this area dy dz, right? Similarly, the amount of flux leaving will be what? Flux leaving is fp x plus dx we got, fpx plus dx, right? And through that area, same area dy dz, so that will also be multiplied with dy dz. Then we are going to find out the net change in number of holes, number of holes, okay, in that differential volume. So net change means what? We can write it as fpx, right? And then the area, through the area dy dz minus what? The value, that is fpx plus dx, right? This, and then dy dz. So this will give us the change, right? This will give us the change in what? Number of holes per unit time, number of holes per unit time, okay, in the differential volume element, right? So mathematically, if I'll write the same thing, I can rewrite it as what? Del p by del t. Okay, del p by del t gives you what? The p is the concentration of holes and the variation of concentration of holes. So p is concentration of holes. Concentration of holes means what? Concentration of holes, we said number of holes per unit volume, number of holes per unit volume, right? So per unit volume. Now if you write del P by del T, this will give you what? Number of holes, okay, per unit volume, per unit time, per unit volume, per unit time, right? Unit time. So you got del P by del T, the variation with respect to time. So that we got here. Now, if I want to find out through that volume dx by dx, this is per unit volume, you can see, right? So this is written for per unit volume. Now, if you want to write it in that particular elementary volume dx, dy, dz, what are the number of holes per unit time? Then what you will do? Del P by del T multiplied with dx, dy, dz. If I'll multiply it, then what it will give me? It will give me the number of holes per unit time. So this will give me number of holes per unit time, right? So if I want to write in terms of concentration of holes with respect to time or per unit time, then what I can write, okay, this multiplied with this dx, dy, dz will give me what? Number of holes per unit time through the elementary volume dx, dy, dz. Okay, this must be equal to what? This value, the net change in number of holes per unit time. Okay, because variation of P with respect to time you got in the differential volume dx, dy, dz is this, right? So I can equate these two. So del P by del T dx, dy, dz can now be written as the same value here, that we got a px dy dz minus a px plus dx dy dz. So taking dy dz out, I can actually write a px minus a px plus dx, right? This, and then dy dz is the area through which that whole flux moves, right? So this way we can write. So rewriting it again, finally what we can write is del P by del X, sorry, del P by del T, del P by del T, dx, dy, dz can be written as fpx, the whole number of holes that enters, okay, at x, and number of holes that leaves, okay, x plus dx per unit time, and through the area dy dz. Okay, this can be written as minus del fp by del x dx dy dz. How we got this? Let me just discuss this. So using this, Taylor expansion, okay, for fpx plus dx. So if I'll write this, this particular term fpx plus dx, okay, let us take this fp x plus dx. This dx is infinitesimally small, very very small. So we can actually use Taylor expansion and keep up to the two terms, okay, that is up to the first order. Okay, so what I will write, I can write this as fp, okay, this x minus, you got this, sorry, so I just expand, I will expand it, then we'll substitute it. Okay, so fpx, okay, then the second term will be what? Del fp by del x into dx. Okay, then 1 by factorial 2 del square fp by del x square dx square. That way you can just keep on writing the Taylor expansion. But let us ignore the second order and all higher orders. Okay, we will keep up to this dx, because dx is infinitesimally small. So dx square, dx cube, all those, will have very very small values. So we can ignore, the higher orders here. Okay, higher that, dx square, dx cube and all. So keeping up to this and then substituting over here, what we can rewrite this equation as del p by del t dx, dy, dz can be written as, we have fpx minus, if I'll substitute this thing here, then we got fpx, okay, plus This is in bracket, so this will be minus. Let me just open it. So minus del fp by del x and tx. Okay, so this is what we got. Then we have dy dz outside. Right now you can see fpx and fpx will cancel, and we will remain with what? Minus del fp by del x dx dy and dz. This is what I wrote over here. Okay, so finally we got that the change in hole concentration with respect to time in the infinitesimal volume, that is dx dy dz, how it is related to what? The variation. fp was what? fp is the hole flux. Hole flux means what? Number of holes. Okay, so del is the variation, so fp is the number of holes per unit time per unit area, right? So now you got this. So del by del x means what? The variation of hole concentration per unit area per unit time, right? So this is how you can just relate this variation of hole concentration. Hole concentration is the variable here. So p del p by del t, and here you got minus del fp by del x. So finally we can write the value of this del p by del t dx dy dz through infinitesimal small volume can be written as minus del fp. Fp is the whole flux, okay, upon del x dx dy and dz, right? So when we said holes are moving from one phase x here at x, and entered at x and left this x plus dx through the area dy dz. If you remember, dy dz was the phase, was the area, dy dz was the area, right? So here we said this is the relation that will be followed. Okay, and this equation we said is the continuity equation, right? So when these holes they move, okay, in x direction, y direction, or z direction, or through that infinitesimal small volume, we said they will undergo generation and recombination. Okay, so simultaneously this the process of generation and recombination will also happen, right? When they pass through this particular volume, right? So the generation rate and recombination rate, if you will consider, which will also affect the whole concentration in that differential volume, right? So if you will consider the effect of these generation rate and recombination rate, we can modify this equation further. So what I will write, the final equation we can write. So what you said, when the holes they move, okay, through this dimension, small dimension, right, or small elementary volume, we said this is the change we will get. In addition to this, the generation and recombination will also affect the concentration of holes, right? So the generation rate and recombination rate also need to be taken into consideration. So in addition to this particular term, there must be two more terms that will involve the rate of generation and rate of recombination. So in addition to that, we will add in addition to this particular terminology or expression, we need to add these two more, okay, effects into consideration to write the overall change in concentration of holes in that infinitesimal small volume, right? So we can modify it further. I can write it as del p by del t dx dy dz. This gives you the infinitesimal volume, can now be written as minus del fp, the whole flux changes with respect to x, okay, if it's moving in the x direction, dx dy dz, right? The infinitesimal volume plus, if I will consider the rate of generation, plus why? Because if there will be generation, more number of hole concentration will be added. So if the generation rate is suppose gp for holes, g for generation, p for hole, okay, in that infinitesimal volume, so gp is the rate of generation, means number of holes created per unit volume, okay, and then multiplied with dx, dy, dz will give you the total number of holes created in that process of movement through that in a small volume. Okay, and recombination means loss of holes. So concentration of hole will decrease. Already we have determined the recombination rate this way: p divided by tau p. I can write tau p. Okay, so p is concentration of holes. Okay, and divided by tau p is the excess magnetic carrier lifetime. So that value for recombination already you have determined in the previous video. You can refer, and dx, dy, dz is the through that volume. So these are the two additional terms we added. Okay, in this. Okay, so the final equation we can write this way. Okay, this is the final equation. Okay, and this is nothing but the continuity equation for holes. Continuity equation for holes. What it gives you? It gives you the variation of concentration of holes with respect to time, and the same variation of concentration of holes with respect to space, right? So this particular equation relates the variation of space with variation of time of a particular variable, and here the variable is concentration of hole, right? So finally you can just write, this, if this is the thing for infinitesimal volume dx, dy, dz. Okay, everywhere you can see this dx, dy, dz in all these terminologies. So per unit volume, if I'll find out, then you can just remove this, cancel this dx, dy, dz, right? So that we can write it finally as del p by del t, that is the change in concentration of holes with respect to time, can now be written as minus del fp by del x, which is given by the whole flux with respect to the space, change in dimension. Okay, change in the x direction, the change in concentration of hole flux with respect to x, plus gp, that is the generation rate of holes, minus p by tau pt, that gives you the recombination rate of holes, right? Tau pt or p, simple depends, I think we wrote, yeah, tau p. Okay, so this way you can write. And then similarly we can write it the same way: del n by del t, that is the variation of electron concentration over time, can now be written as del f n, electron flux over the space coordinates. Okay, change over the space coordinates, gn, the generation rate of electrons, right? Generation means addition of electrons, more number of electron concentration, and recombination again same, n divided by tau n we can write. This is the recombination rate. So finally we can write these two equations, which are known as the continuity equation for holes. This is the continuity equation for holes, and this is the continuity equation for electrons. Okay, so when the electron is moving or the hole is moving in a small dimension through a volume, then how the concentration of electron or hole will change, okay, with respect to time, that can be determined by knowing what amount of flux change with respect to that direction, in a particular direction, x, y, or z. This is one dimensional. We considered it is moving only in x direction, so we need to find out the whole flux, variation of hole flux in x direction only, plus the rate of generation minus the rate of recombination, because these two processes are also going to affect the concentration of holes, right, or electrons. Okay, so this is all about this video. Continuity equations for electron and hole we defined in this video. Now in the next class we will come with a new video. Okay, thank you for watching. Stay tuned.